All right. So we discussed the basic concept behind the 7-segment display operation and also discussed the NAND-NAND logic family. And the take-home message was any random Boolean logic could be converted into a NAND-NAND platform, right? That is so powerful, as I hope I mentioned that. So this was the last slide that we actually kind of touched upon, but obviously we rushed through it. So I will repeat it again, and hopefully it will be a good practice for all of us. So here, we are going to convert a given Boolean function to a NAND-NAND logic family, all right? Without any loss of generality, honestly. This could have been any Boolean function. But since we discussed the 7-segment display anyways, we decided to use one of the 7-segment display output function, which is A, for example, to do this exercise. So it's kind of binding the both, both concepts. Okay, so if you go through the K-map optimization that we also discussed in the last class, you end up with this function. Excuse me. This function for output A for the 7-segment display. All right. Now, the first thing that we should do is implement that using the conventional AND OR based logic that we all know and can easily relate to. So first, we'll start with the ANDs. So this is an AND, this is an AND. Let me do it this way. So you have X, Z, and then you have X prime, Z prime. Notice you don't have, for the other inputs, this one, there is no AND necessary, right? As you see, this is just gonna be directly given to the OR gate. These are just direct inputs. So we need an OR gate because we need to accommodate this plus. So how many? 1, 2, 3, 4 input. So let me do this 4 input OR gate. 1, which is this one, 2, which is this one. And for the other two, we need to have W and Y. And this is your functional output A. Are you all good? Okay. Now, the most important concept that we should keep in mind when it comes to converting a logic family into NAND is that when you have an OR gate with inverted input, say for example, A, B, I mean, when I draw the bubble here, it basically represents that you have an inverter. Okay, it's just an easier way to represent it. So this is your OR output. So when you do A prime plus B prime, it's going to be the same as doing if you just take AB and do a NAND. So AB prime. That's the whole concept, right? So I'm trying to convert the OR gate into a NAND gate. And to do so, I have to invert all of its inputs. And how can I do that, folks, without changing the logic? Help me out here. So let me change the color. So whatever output this one gives you, if you add an inverter, will everything still remain the same? If I just randomly add an inverter, will everything? No, it will disrupt the logic. So what should I do to make sure nothing changes? Add an extra second inverter. Exactly. So basically in the same chain, I will add a second inverter. So if I add 2 inverters, it's as if there's nothing there. Are you all good? In terms of logical function, nothing will change. Okay. All right, one more thing. How about this one? If I add an inverter here and another inverter here, will anything change? No, in terms of logic, no. Same here for Y. If I add an inverter here and another inverter here, nothing will change. For W, if I add an inverter in this chain and other inverter right here, nothing will change. So I'm basically adding a pair of inverters in every line. Now, look at this one. Can I say that for this OR gate, all of the inputs are inverted? So it's all the same if I replaced this with a NAND gate instead. Are you all on the same page? Okay. So I am going to now replace, let me not completely erase this. Let me draw it on the side. So for this one, we will end up with a NAND gate, which is represented by this bubble, right? And then you have 4 inputs, 1, 2, 3, and 4. Let's take a look at this one, folks. So instead of showing this inverter, can I use W prime as an input? My input is basically W prime. Okay, my input is W prime here. All right, I changed the literal actually. Here, instead of an extra inverter, can I use Y prime as an input? All right, okay, then I hope it's readable to everybody. Folks at the back, can you see this still? Okay, all right. How about this one, folks? What is this gate? So you have an AND and it is followed by an inverter. Essentially, you are getting NAND. So can I replace this as a NAND gate? So you have a NAND gate and your inputs are X and Z. And again, for this one as well, you can replace it as a NAND gate. So you have a NAND gate and your inputs are X prime and Z prime. Okay, sorry, it's a bit congested here. Alternatively, I can also redraw it. Yeah, don't worry. There is a, there is an animation that will show you the entire circuit eventually, so you can study at home. But for the sake of our discussion here, let me also try to redraw right here. So you have an AND gate, you have W prime, you have Y prime, and then you have X and Z and a NAND gate, and then you have X prime and Z prime. Okay, now tell me, if I try to get the logic function, so apparently nothing will change, right? As you can imagine, nothing will change in the output. But if I try to represent that in a logical format based on the NAND-NAND platform, how will it look like? Help me out. So that's exactly what it asks you to determine NAND-NAND Boolean expression. So in terms of the truth table, nothing will change, but the expression will be different when you represent it in terms of and or versus when you represent it in terms of NAND, only NAND. Okay, so here is what I mean by that. Tell me, what is the output of this one? Let's do it together. How should the output look like? This is X prime Z prime. No, this is XZ. Sorry. Let me make sure that we do it the right way. Okay, all right. So can I say this is XZ prime, folks? Whole prime, like this is an AND, right? So you do an AND and then you take NOT of it. It's not, be careful, it's not X prime, Z prime. It's X, Z whole prime, right? So I can also use a parenthesis just to make it clear. So you do an AND and then you invert it. That's why it's NAND. How about this one? This is X prime, Z prime, whole prime. I'm changing the prime just to make it easier to. Are you all good? Okay. All right. Now, how about this one? This remains the same, W prime and Y prime, nothing changes. Okay. So the only logic gate that you have used in this circuit is what? NAND gate. Or you have just direct inputs. But if you have to use a logic gate, it will be NAND gate. That's the whole point. Now, how about the output of this final NAND gate, folks? First, don't think about the NAND. Treat it like an AND gate. Okay, AND. So what are my inputs? First, I have W prime. I will end it with Y prime, the second input. Then I will end it with the third input. What is my third input? XZ whole prime. And then I will end it with the fourth input, which is X prime, Z prime, whole prime. So I have taken an AND of all 4 inputs. Now what? It's essentially a NAND. So whatever the final expression I get, I have to invert it again. That's the final A. Does that make sense? Does that look easier or more complicated than the usual? Of course, more complicated, as you see. So typically, you never have to deal with this type of expressions, honestly. You could always come up with an AND OR gate first, and then convert it into NAND fashion. Yes. Yeah. It's a great question. So typically, if you just use one kind, there are multiple arguments. There is no easy answer. So he asked between these two approaches, like if you use AND gate and OR gate versus only NAND gate, which one is more efficient? All right. Easy answer is NAND gate, obviously. There is a reason why we try to always do NAND-NAND operation, but it is difficult for me to explain exactly why that is the case if you don't go through the CMOS logic design approach. But I mean, I'm almost tempted to talk about it. So remember, okay, let me just quickly try to explain this to you. In conventional CMOS-based Boolean logic design circuit, you always end up with NAND, and there is the reason. And I can give you the high-level argument. The reason is you use two type of MOSFETs, NMOS and PMOS. Okay, so let me show you how the NAND gate looks like. A 2-input NAND gate looks like this. You have 2 NMOSes and 2 PMOSes. This is how the PMOS looks like. You have a circle at the gate terminal. Okay, you have the same inputs A and B. This is your VDD. This is your ground. This is your output F. That's how a NAND gate looks like. NAND. So basically, you start with NAND. If you try to get an AND, you take an invert of this. So what you do is basically you get a NAND and then you connect it to an inverter. This is how an inverter looks like. So you need 2 more transistors to get an inverter. And then you get the function AND. So this is your AND and this is your NAND. So based on the conventional circuit design approach that we have to live with in CMOS world, where we are living in CMOS electronics world. To get an AND, we first need a NAND, and then we make it into an AND. You see? So we need 2 extra transistor to convert an AND into a NAND. Are you guys all good with this or no? And there is a reason, and I can like very high level tell you. Imagine if you had a question, why do we have the NMOSes right here below and PMOSes above it? What if I flip it? If I put the NMOSes on the top and PMOSes below, that solves this issue. You no longer need these other 2 transistors. Okay, this is how, but there is a reason why we cannot do that. We will always have to use NMOSes below and PMOSes at the top. NMOSes are good to work with ground. PMOSes are good in terms of working with VDD. That's why. Okay, and I'm not giving you any other reason because of the interest of time, but because of the way we design the circuit, we have to design the circuit. We have to live with NAND mostly because that makes it efficient. If you save 2 transistors per gate, just imagine when you have millions of gates, you'll be saving millions of transistors, which is a big deal. All right. So to answer your question, NAND-NAND operation is typically always better than AND in our standard. But if you magically, I mean, there is a reason why it's not an easy answer. If you come up with an alternative platform, like as I told you, superconductor-based logic gate, right? They are no longer limited. You don't even have any transistor there. Okay. You don't even use any transistor for superconducting logic. So in that type of circuit, you don't know, like NAND or AND, it might be completely the same. So in that case, it doesn't make sense to just try to push everything to NAND. All right. So simply because of the CMOS world, we have to live with this NAND-centric design approach. But it has nothing to do with the Boolean logic. If anything, the Boolean logic looks more complicated for the NAND option versus the AND option, right? Any other questions? That was a great question. But the problem is we are still not there to fully understand this. But I told you all the right points. So these are the actual reasons why we cannot do it. Okay. And I'm more than happy to go deeper during my office hour. And I'm almost tempted. Okay. So this is basically what we covered already. And this is the final outcome. This is easier to type prime, like using like this type of approach rather than a bar on top. So you see, this is like full of primes. All right. Okay, so that concludes this lecture. And you now know how to convert any logic into a NAND-NAND format, hopefully. And if we have learned something by going through so many K-maps together, right? The more variables you have, the more complicated and time-consuming it becomes. And at some point, when we went to 5-input K-map, you already had to divide it up into 2 K-maps. And there was a question about what if we have 6 inputs? Then we would need 4 k-maps, four variable k-maps, right? And that's pretty much it. Like if you try to go to 7 or 8, at some point it doesn't make any sense at all. Okay, there are multiple problems with the k-map based optimization approach. So we need an alternative. Okay, and we will talk about the alternative today. Uh, Let me start with this. You can read it at home. I have already covered most of it, but just to be very quick about it, K-map is more like an art, in my opinion. It is a pen and paper approach. So you really need manual intervention. You have to think about it, right? It's very difficult to come up with. It's actually impossible to come up with a real algorithm that you can code into a computer to make it do it. Does that make sense? I mean, it's not impossible, but it's not very straightforward. Okay, so, well, it's not the best solution. So people started when Boolean logic started becoming more complicated with enhancement in hardware. Remember the first lecture where I showed you we at some point used to have 1,000 transistor on a chip, so nobody cared. But now we have billions. So definitely whatever used to work like 60 years ago will no longer work. We need computer-aided design, and for that we need an approach that will be more favorable for coding. So that's why people thought about different approaches, and two scientists or engineer, one from Harvard, one from Stanford, both of them were academic, as you see, they independently came up with a tabular approach. So an approach to use tables to come up with this optimization of Boolean functions. Okay, so they are both credited for the discovery and invention of this approach, and that's why the name. So they are basically two different people, Quine-McCluskey. Okay, so they basically jointly developed this approach that we are going to learn together. Okay, it is going to be, and I don't want to make the comment right now, but okay, I will make it. As we go through the process, you'll feel that it's tedious, it's stressful, it's difficult to keep track of, it is time consuming. And that's exactly the point. It is not supposed to be done by human manually. It's meant to be coded in and the computer will do it in a microsecond, right? But for you, it's like, oh man, how can I keep track of all of this? But if you don't know the approach and algorithm, then you cannot code. So that's why we have to understand the approach together. And if anything, if you're wondering, I mean, I probably shouldn't tell you this right away, but I'm not going to test you in your exam with this particular approach, simply because of the reason of it taking too much time and too much real estate. You probably need multiple pages to just work on it. And you could have used a K-map, honestly, to achieve something with like 1/5 of the time, given that you have like 4 variables. But if I give you now 15 variable, the same approach will work for Quine-McCluskey, but K-map will like literally die. There is the difference, right? Okay, but for this, for the sake of demonstration, so that we could finish it within the real estate of a slide, as well as the time frame of a class, we chose to use an example of just 4 variables. So I'm just telling you before, for 4 variable, it doesn't even make sense to use this approach. It's so complicated. But the approach doesn't change. If you go for 4 versus 40, it's going to be the same. So are you ready for it? Please pay attention so that you don't have to read through pages of textbook, which will probably confuse you even more. So if you pay attention to what I say, it will hopefully be way easier for you to try it out at home. And I'll make you practice for a homework problem. That's all. I'm not going to test you in an exam, right? It's not feasible. All right, let's do it. So for this approach, you need to begin with this, mean term expression. You remember we can represent a Boolean logic in different way. I can give you a truth table. It's fine. If I give you a truth table, can you come up with this expression, folks? Right? Just look at where the ones are and just put them there. That's the mean term. Sum of mean term expression. That's all. That's exactly where this approach begins. If a function is not given in this way, like if it is given in a way like a prime bc plus blah, 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 right? In a functional format, you have to convert it into this mean term format. It is not difficult to do, honestly. And we have seen that in the past. I'm not repeating it. So as you practice more and more, you will have it on top of your head. Okay, I can convert any type of functional representation, either in an algebraic format or a truth table format, into a minterm format, like this, sum of minterm. So that's where our adventure begins. So when you look at this minterm expression, what does this number mean? Like 6, 7, 8, 9, 10. What do you think they mean? They mean there is a 1 at that point. If you prepare a truth table, there will be a 1 at the 10th row. Basically, it's an 11th row because it starts with 0, right? So this is the first row. There will be a 1 at the first row. There will be 1 corresponding to 6, which is the 7th row, and something like that. So we are all on the same page. Okay. So, and there are 4 inputs, so there will be how many? 16 rows in total. Okay. Now, what we're going to do is we're going to convert all of these minterms in binary. Can you do it? If you have a truth table, it's already converted in binary. Just visualize it, right? So for example, 0 will be 0, 0, 0, 0. Why am I using 4 zeros? Because it's a 4 variable combination. So I'm going to use 4 inputs, 4 bits, all right? How about 1? 1 will be 0, 0, 0, 1. How about 2? 0, 0, 1, 0, and so on. Can I convert all of these numbers into binary? Okay. All right. Stay together, all right? Don't go off the trail. Like if you feel like, hey, wait for me, I'm lost. I'll repeat and I'll let you catch up. Are we all together yet? I mean, we are heading into the situation where things will be complicated. Okay, so it's super easy. Convert all of these numbers into their binary format. So now visualize that you have a list of binary. It's not the whole truth table. It is only the numbers that are showing up in the minterm expression like this. You don't need the whole truth table, only the numbers that are listed here. Once you get the list of numbers, binary numbers, I am going to categorize it into different groups. Based on what? Based on the number of ones. Are you still with me? Not serially, not like the way we do our truth table. In a truth table, we just do everything in incremental series, right? 0, 0, 0, 1, 0, 0, 1, 0, blah, 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 right? They will always be in sequence. But no, that's not what I'm going to do right now. I'm going to group them based on the number of ones. So for example, group 0 will have no one. And it will have just one member, which is 0, 0, 0, 0. There are no other numbers like this, which has absolutely no one. Okay. The next group, which is say group 1, will have the numbers that have just one. Sounds weird, but just one. You see that? And there are numbers like this: 0001, 0010, 1000, something like that. And the next group will have the numbers that have 2 ones. Okay, so for example, this is a number that has 2 ones. This is another number that has 2 ones, but they're in different position. But at least there are 2 ones. Okay. Finally, group 3 will have. Let me show you. 3 ones. And imagine for a second, if I gave you 15 here, like in the list, then you would have another group, group 4, with 4 ones, and that will have just one member, which is like 1, 1, 1, 1. All right. Are we all on the same page still? Folks at the back doing what? Okay. All right. Okay. So you have groups. It's not too difficult. It's easier to handle. Fine. So we group them. Next one. And by the way, all of these are mentioned here. You can read it at home or when you practice. You don't have to read it now. I'm explaining anyways. So let's move to the next one. So what we have done so far is we have taken care of first column of this step. First column. We have grouped them into different steps. Now, the next step is comparison. We'll compare them with each other. And what are we looking for? We're looking for 2 entries that differ exactly in 1 bit. When you take 2 numbers, as long as they compare in 1 bit, you can group them together. You can merge them together or something like that. Okay? Here's what I mean by that. So let's take the first one. This one. Do you see any similarity here? I'm looking for just 1 bit change. Doesn't that sound like something related to K-map, folks? K-maps are organized in a way that between neighbors, there is just one variable difference, similar to that. Basically, they're all the same thing. They're dealing with Boolean logic and optimization. So there will be commonality. Okay, so you take the first number 0, 0, 0, 0, and you compare with the second number, which is this one. You see that there is just one bit that changes, which is the least significant bit, right? Does that make sense? So I will group them. I'll group them this way. Take what is the position of this number. One thing that I probably didn't mention. Let's move to the previous slide. I didn't just group them for the sake of simplicity. Second, it's not letting me erase this. Okay, for the sake of simplicity and easier reference, I also converted them into the corresponding decimal. You see that? And this basically, these are the mean terms. So what does this 9 mean? 9 is basically the decimal representation of this number, so that it's easier for us to compare and group them. Are you all with me? Okay, so let's move there. So I'm going to write, I will take this member and group it with the next one, 0, 1. And whichever variable varies, so this location varies, I'm going to remove that and place a dash. Are you guys all with me? Okay, if you are wondering, is it too random? Like, are we just doing it like black magic or something? Right? So basically, there are logic, mathematical logic behind all of it. I mean, I'm tempted to tell you one example so that you don't feel like, you know, you have absolutely no logical basis. Let's consider this. Imagine if you had A, B, C, D. Okay. Imagine when all of these variables remain the same. When you compare these two terms, they're essentially A, B, C, and for this one, it's going to be D, and the other one was D prime. You see what I mean by that? So the only change that you have between these two terms is one of the variables was primed in one entry and not primed in the other entry. Others are exactly the same. So A, B, C, D and A, B, C, D prime. So if you add them together and take A, B, C as common, what do you have? D plus D prime. What is D plus D prime? 1. So it's basically gone. So you can combine them into A, B, C as if D is gone. Can I write it this way? And that's exactly what we're trying to do without realizing. But if you try to always relate it to this underlying Boolean algebra, you will probably become really, really stressed out. So I'm just giving you steps to do, like shortcuts kind of things. And that's exactly how the computer doesn't care about algebra. It just tells you, it just does what you tell it to do. And that's exactly how things are coded. If you have just one bit mismatch between two rows, discard the bit that changes. So basically you discard it. This basically represents you have discarded that bit. And you combine them into it, right? Okay, let's take one more example. So let's compare the same entry with the next one. Folks, can I group these two together? 0, 2. Why? One bit that changed. And where is that bit, folks? Third from left or second from right, right? I mean, depends on how, like my right or your right, but you get the point. So it's basically this bit that is changing. Okay, all right. So I'm gonna group them together like this, 0 and 2, and I will just use a dash for the bit that changes. Okay, what's next? Can I group 0 and 8? Yes, because there is just one bit change. 0 is a very easygoing player. So honestly, it's easier to deal with 0. Okay, now what? Okay, so I've grouped all three together and I've taken dashes in the places of bits that was changing. Now, can I do this 0 and 5, folks? Like I'm basically going to the next group. Can I do that? Why not? There are two bits that are changing, right? Okay, so I can keep checking this 0 with all the other bits. Should I do that? I can, but I don't have to. You know why? Because that's how we chose. When we group them together, there is already one bit difference. I mean, if you go to the neighboring groups, only then you have a chance of having one bit change. But if you go to a group that is not even your neighbor, there will definitely more than one bit change. Don't you think? Because there are more ones. right? Just think about it this way. Like this will save you time. You could always do brute force, compare everyone with everyone. That's fine. But that's gonna take more time. But if you realize that there is 0, 1 here, at least 1, 1 in the group 1. But there will be 2 1s in the second group. So between 0 and 2, we have already more than 2 bits difference. Don't you think? Sorry, more than 1 bit difference, at least 2 bit difference. So there is no point of comparing a group, say group 0 with group 2 or group 3. So I'm never going to even try to compare group 0 with group 2 or 3. None of them will work. If you can try and you'll see none of them works. It's fine. So the only things that we have to compare against would be, say, the neighbors with each other. Say group 0 with group 1, and then group 1 with group 2, and group 2 with group 3. Even then, not everything will lead to a grouping. And I'll show you examples like that. Are we still together? Folks, don't give up. All right. Okay, so let's do the second round. Let me actually fast forward and do a group 2 versus group 3 comparison, because that's where you start seeing things that don't add up, right? For example, can I compare 5 with 7? Let's see. Why? Notice these 2 numbers. Which bit varies? Just this one, right? There's 1 bit variation. So I will take 5 and 7 and I'll just dash the one that varied. Okay. All right. But can I take 5 and 14 now, folks? 5 and 14. Why not? Because if you see, you have a variation in this bit and you also have a variation in the second bit. So there are 2 bit variation despite them being neighbors, and they have the same number. Like, I mean, they don't have the same number of ones. The number of ones differ by 1, but because of the position of those ones, you have 2 bits that differ between these 2 numbers. So will I take this combination 5 and 14? No, I'll not take them. So that's exactly why I fast forwarded to show you don't now you have to compare, by the way, no exception. Between the neighbors, you have to compare all possibilities. So after you compare all possibilities, we find only 4 cases, right? You see my point? Just can you tell me how many comparisons we have to do when you have like 4 members here and 2 on the other side? 8, don't you think? For every one of this number, I'll have to check 2. So if you have 4 of these numbers, you have to check 8, right? But then you end up with just 4 combinations that work. Are you all okay so far? Okay. Now, so let me just quickly repeat myself. You first group them based on the number of ones, and then you are grouping them based on wherever you get just 1 bit change between 2 entries. And you can either take a brute force approach and compare everyone with everyone. Doesn't hurt. Things will work eventually, but it will take you a longer time. If you write an algorithm, it will be a crappy algorithm. It will take way long time to eventually do the job. So better to only compare the neighboring groups with each other. And within the neighboring group, not all the combinations will work. Some of them will work, but you still have to do brute force between these neighboring groups because you don't know which one will match. Okay. So at least within the neighboring group, you can do brute force. Okay. After that, you end up with, these situations. And by the way, why do you have these ticks? These ticks are important. None of these are like useless here, by the way. When you use these ticks that represent, you manage to somehow group this with another guy, another entry, somehow. And all of the entries were grouped with at least one other entry. Okay, so when you group them, you just tick them at least. And you will see why that tick is important. I'll show you in a second. But if you manage to group 0 with someone, say 0 was grouped with 1. Okay, sure, tick 0 and 1. Yeah, you needed to use 0 again with 2, but you don't have to tick it again. It has already been marked. Fine. So it has been used at least once. If there is an entry that cannot be used even once, that's something to think about, and we'll come back to it. Okay. that typically doesn't happen in the first column. It will happen in the second column, okay? But the point is, if you can manage to use one of the entries for any kind of grouping, you mark it with a tick. Done. For a computer program, you flag it, say flag 1 or flag 2, something like that. It has been used at least once. Okay, so do we know how to go from column 1 to column 2, folks? Are we at least all clear on this part? Going from column 1 to column 2 by grouping different entries together. Okay, so now how do we go from column 2 to column 3? We'll have to further group the entries using the exact same logic. You have to compare different entries with each other and find the ones that differ just by one position, just one, exactly the same approach. Nothing changes. And you treat the dashes as an entry, by the way. So dash is treated as a dash. Wherever there is a dash, you need a matching dash in the other entry as well. Okay, so now it becomes easier. You know why? Because you can just look for dashes. You don't have to look for zeros and one first. First, look for dashes. If they don't match, no point in comparing. Okay, so let me do it for you for once. So for example, I'm going to take this first entry, 0, 1, and look at where the dash is. Compare it with its neighbor. Where do you find a matching dash? Just in one location, right here. You see that? So all the other points I don't need to care about. So it will get easier as we go down the chain, of course. The first one is the busiest. As you go down, things will basically gradually ease up. So if you see this dash, the only other dash that match with the neighbor is this one. So can I now, I mean, it's not done. At least the dash matched. We'll have to see the other entries as well. But this is an easy trick to look for the dash first. Okay, now do you see that there is a 1-bit difference between these two entries? Can I group them? So when I group them, I have 0, 1 and 8, 9. So 0, 1, 8, 9. That's how you group them. Like just basically use the numbers to identify them. Okay. So 0, 1, 8, 9. And then wherever you have a mismatch, just use another dash. So now you have two dashes, dash, dash, 0, 0. Does that make sense? Let's do one more thing. Okay. So apparently no other dash will match with this dash for 0, 1. So let's move to the next entry, 0, 2. Oh, will I compare this 0, 1 to the other group? No need, because they're never gonna match, right? There will always be more than 1-bit difference. Okay, so let's do the second, 0, 2. Just look for the dash. And can you help me find a matching dash? Folks, I found it. Can you see that? There is a matching dash, at least with just one entry. So 0, 2 and 8, 10. 0, 2, 8, 10. That's the group. And where do you have the mismatch? I have the mismatch here in the first bit. So you use dash 0, dash 0. Are you all good? Okay. So basically you repeat the process. You repeat the process and you go through the chain. And after you go through the chain, like you do, like first of all, take every one of these entry, compare it with its neighbors. You're done. Then take every one of these entries and compare it with its neighbors. And then you are done. So that's why you end up with two groups. See, this group comes from this comparison. The second group comes from comparison between 2 and 3. You see that, folks? Okay. And if you have, imagine if you have 20 variables, how many groups do you think there will be? Like many. So this will go on, like only then it will make sense. Like you'll completely give up, man, I cannot do it manually. But you can easily write a code so that a computer does it. Okay. All right. So now after you have grouped it once, practically you just keep going using this approach. And then you see the next set of comparison with just 1 bit and 1 bit and 1 bit. But here we have already arrived at a situation. Notice that none of the dash will match with any other. Okay, let me show you. First of all, are you okay with going from column 2 to column 3? Tell me first. We are okay with that? Okay, we can go from column 2 to column 3. Just before I tell you the other thing, let me point out a few things. Some of these entries have been crossed out. Why is that? Because if you haven't noticed, they were repeated. Say dash 00 dash dash 00 dash. Why are they exactly the same? Exactly the same. Why? Because we use the same combination 0819 0189. Basically, they are the same. They're in separate sequence, but they are basically the same thing. So they are repetition. Are you doing okay so far, folks? All right, let me show you how we arrived at it. So if you take this 01 and take this 89, you end up with this entry 0189. On the other hand, when you go to this point 08, okay, and then take 2 and 10, yeah, I mean, all you are doing is comparing. You don't know how things are going to end up. After you finish comparing, you see both of these ended up. This one ended up here, and the green one also ended up here, but they're essentially the same combination in different sequence. So there is no point in using the same thing twice. Do you see how we arrived at this repetition, folks, or no? Just by doing your job of comparing different entries, after you group them, they end up being the same. So you don't need to use them twice. Just get rid of one of the entries. So this 0819 and 0189 are basically the same thing. You keep one of them, whichever you like. So we keep the one that we found before. We remove the one that came later. And same thing applies to this one. Notice 08210 and this is 02810. Essentially the same thing. If you rearrange them, they're the same. So you get rid of one of them. And finally, this one as well, the repeated entry. So you get rid of the repeated entries. So you're left with the entries, this one, and this one, just 3. Now, just take a look at the 3. And do you see any option to have just 1 bit difference between any of them? Every time, if you compare this one with the other one or this one with the next one, there will always be more than 1 bit difference. So you cannot simplify it any further. Does that make sense, folks? We're almost there. Don't worry. We're almost there. Okay, so that means that's where you stop. But if you could further group them, you would have done one more step, column 4, column 3, and things like that. But now we have to stop because we cannot group them any further. So after you arrive at the group, have you noticed something that I haven't covered yet? I told you that check marks are important, right? So when we group them into this column 3, if we could manage to use one of them, say 01 and 89 were grouped. So when we use them, we check them out like this. Say, hey, I used them at least once. Similarly, when you use 02 with 8 and 10, you mark them as done. And you keep doing it for all the entries. You have to, that is important, very important. Don't forget it. Don't forget to use tick marks. After that, there are entries that were not grouped with anybody else. Okay? For example, this entry, say 67 or 15, we couldn't find any other entry with which it will match in terms of just 1 bit difference. Okay? So since it didn't match, we didn't tick it out like this. We didn't use any tick marks. So they are left. Are you all with me? And I told you, I warned you before that after we go through you'll probably be, why are we even doing this? By now, we would have probably, with K-map, this could have been taken care of like with 5 minutes, I guess, right? But now, that's the whole point. That's what I'm trying to tell you. Okay. So now, look for the ones that haven't been tick marked, not tick marked. So this one has not been tick marked. This one has not been tick marked. This one hasn't been tick marked. And what else? 1, 2, 3. These ones have not been tick marked. So how many do you have that are not tick marked? 6. Obviously, the final group will not be tick marked. That's where you stop, basically, right? So none of these will be tick marked. So the final group and also the ones that were not tick marked before. So you have 6. So you have to, these are basically your prime implicant. Okay, basically these will represent your prime implicant. You have to take these variables and move to the next one. And let me show you how to get the implicant corresponding to this before I get to the next slide. So look at this one, dash, dash, 0, 0. So wherever you have dash, those variables will not be there. They're omitted. And so remember, A, B, C, D are your variables. So you have 0, 0 corresponding to whom? B and C. So I will have B prime, C prime for this one. And what is the next one? A is omitted. B would be what? B is 0. So B should be B prime. C is omitted. D should be prime. B prime, D prime. Do you see that? No? Okay. So let me move to the next slide as well. So B prime, C prime correspond to 0189, which is 0189, as I showed you. Okay. Let's take one other example. 2, 6, 10, 14. What is that? 2, 6, 10, 14. It is dash, dash, 1, 0. So A and B are gone. C would be C because it's 1 and D would be prime, CD prime. Can I write it this way? So that's CD prime. How about this row? Let's take one of these rows. This one. Can anybody help me write this one? What is A? A prime. Should there be a B? No. How about C? C prime. How about D? D. A prime, C prime, D. So A prime, C prime, D. Can you do this for all 6? Okay. So you have done this for all 6. All right. So now you list them this way. You take the groups, you convert them into min-term format, and now you create another list, another chart. Remember these numbers, folks? Where did these numbers come from? 0, 1, 2. This is the function that was given to you, the min-term, list of min-term. So you basically put the list of min-terms here. It is not difficult, honestly. If I tell you what to do, you can do it, honestly. It's not like overwhelming or anything, I think. If you follow the instructions, step 1, step 2, step 3, it's super easy to do. So you just create a list with all the min terms listed here. Now, work with me on this. We are almost done. Work with me on this. So look at this number. You have 0, 1, 8, 9. Cross out the corresponding number. 0, 1, 8, 9. You see that? Can you repeat this for the rest of it for me? Let's take one other example. 2, 6, 10, 14. Where is 2? That's 2. 6, 10, 14. You see that? Just put a cross corresponding to the numbers that you have here. Okay, so you end up with this new chart. Are you all with me? Okay, look for an entry that has only one cross in the column, like this. 9 and 14 has only one cross in the column. You see that? So take the row corresponding to the cross. These are your essential prime implicant. Remember, in the K-map format, I told you, if there is a 1, that is only covered by one prime implicant. Remember, we had this discussion, and that prime implicant will be an essential prime implicant. So it will definitely be taken into the function, right? So similar, we are using basically the same thing. If you have just one cross in the same column, the corresponding row will be an essential prime implicant. So these two are your essential prime implicant. So how do you treat the essential prime implicant, folks? You take them into the function already. Just B prime, C prime is already there. And what is the other one? CD prime is already there. So if you go to the next function, B prime, C prime, and CD prime will already be there. Are you all good? We're almost done. Give me like 1 more minute. Sorry. We have 1 minute left and 1 more minute. So 2 minutes. Please. We'll be done. Don't worry. All right. So let's see. After you take care of all these prime implicants, say this one and this one. Okay. This is the fun part. Ready for it? If you when you cover a row, any cross in the same column vertically will be taken out. Like, say, for example, this all the crosses here, here, here. You see my point, folks? So it's drawn here. I mean, I don't have to draw it again. So for example, this one, we took this row and the other row. So the cross corresponding to this one, the cross corresponding to this one, corresponding to this one, this one, this one, this one will be taken out. Everything in the same column will be taken out. Are you all with me? Or no? So just, it's like a game, like a Tetris game or something, right? If you draw a line and any cross that comes above it or below it will be taken out, corresponding to the crosses that show up. But notice, these crosses are not taken out. Why? Because you didn't have any matching cross in the rows that you selected. Did you? You didn't have any matching cross there, did you? No. So only these crosses remain. Folks, just by using these two rows, we managed to get rid of all the crosses except a few. So I have to find a way to take care of these crosses as well. Let me show you. And let me give you the answer. So I'm going to take this row. If you select this row, you can take out these two crosses, and these two crosses will allow you to take the other two crosses as well. Don't you think? So I will be taking A prime BD and add it to the function. That covers all the crosses. Okay, so there you go. That's your optimized function. It's an overkill. All right, thank you. So there is a problem for you to practice. We will practice it together in the next class as well. At least we have seen one complete example. All right, thank you. I'll see you on Monday.